Hello there, my name is Declan. In the next 20 minutes or so, I will be talking about the problem of representing two-dimensional partial differential equations as partial integral equations and the subsequent stability analysis that this allows. So the problem that we're interested in is that of analyzing stability of linear 2D PDEs, such as this 2D heat equation here. Now here we are looking at Lyapunov stability of the system, where we use the L2 norm to define the stability, where L2 denotes the space of square integrable functions. Now to verify stability, we will use Lyapunov's second method. So we will look for a positive definite function v, which decreases along solutions to the system. Now to this end, we will actually take inspiration from the ODE framework for stability analysis. So for an ODE defined by a matrix A, we can parameterize a quadratic Lyapunov function by a matrix P, and then the derivative of this Lyapunov function along solutions to the system is also quadratic and parameterized by a matrix Q. This allows us to then test stability of the system by verifying feasibility of a linear matrix inequality. Now here we're really using a crucial property of matrices, namely that they form an algebra. That is, the product of any two matrices is a matrix, and the sum of any two matrices is a matrix, ensuring us that if we choose P here to be a matrix, Q will be a matrix as well. Now extending this then to PDEs, where we have an infinite dimensional state U and an operator A, we can still test stability using a quadratic Lyapunov function, and then we arrive at this operator inequality for stability. That is, we can verify stability by proving positivity of this operator P and negative semi-definiteness of this operator Q, similar to our linear matrix inequality for the ODE. Now the first question that we run into then is how we can actually define a set of operators P to parameterize these Lyapunov functions. And in particular, just like for the ODE case, the set of operators P should still form an algebra. That is, we should be able to multiply these operators, we should be able to add these operators if we hope to derive similar stability conditions as that we have for the ODE case. So then how do we define such an algebra of operators to parameterize these Lyapunov functions? Well, for 1D PDEs, we actually already have such an algebra, namely that of 1D partial integral or pi operators. So these 1D pi operators act on functions in just one spatial variable x, and they are parameterized by three matrix valued functions, each contributing one term to the expression. So we have a multiplier term, an integrator on the lower half of the domain, and an integrator on the upper half of the domain. Now clearly this operator is linear, so the sum of any two 1D pi operators will be a 1D pi operator as well. And in addition, the composition of two 1D pi operators is also a 1D pi operator. That is, if we can represent B and D here in this format, then we can represent their composition R in this format as well. As such, these 1D pi operators form an algebra, and so we can use them to parameterize the Lyapunov functions for 1D PDEs. Now to extend this then to 2D systems, we consider the composition of a 1D pi operator along the x direction and a 1D pi operator along the y direction, yielding a structure like this one. So where the 1D pi operator is parameterized by three matrix valued functions, the 2D pi operator is parameterized by 3 times 3 is 9 matrix valued functions. And here in each row you can recognize the structure of a 1D pi operator along the x direction, and in each column you can recognize the structure of a 1D pi operator along the y direction. Now clearly this operator 2 is linear, so the sum of any two 2D pi operators will be a 2D pi operator. And it turns out that the composition of two 2D pi operators is also a 2D pi operator. Thus, these operators form an algebra. So with that, we then have an algebra of operators which we can use to parameterize Lyapunov functions for 2D PDEs. Unfortunately, actually using these operators to test stability of 2D PDEs, like this heat equation here, we still run into several issues. First of all, PDEs are defined using differential operators. So even if we parameterize our Lyapunov function by a pi operator, the composition of this operator with the differential operator A need not be a pi operator, and therefore the derivative of the Lyapunov function along solutions need not be parameterized by a pi operator. In addition, solutions to the PDE have to satisfy certain boundary conditions and continuity constraints. Therefore, stability requires this derivative to be negative only for u within this set X, defined by these boundary conditions and continuity constraints. However, merely enforcing negativity of this operator Q, we will be enforcing negativity of the derivative everywhere, thereby introducing significant conservatism. So to avoid these problems, then, we need an alternative representation of the system, namely a representation that is parameterized by pi operators, so that this operator A and Q here would be pi operators, and one that incorporates the boundary conditions and continuity constraints into the dynamics, so that negativity of this operator Q here is necessary as well as sufficient for this derivative to be negative along solutions. Now, to arrive at this alternative representation, we first represent the PDE in a standardized format. In particular, we note that any linear second order 2D PDE can be represented using these 9 matrices. So 9 matrices A00 through A22, each describing the contribution of a particular spatial derivative of the PDE state to the dynamics. So note here that with each column we're increasing the order of the spatial derivative along the x direction, and with each row we're increasing the order of the spatial derivative along the y direction. So for example, for our 2D heat equation, we can represent the system in this format by setting all parameters equal to 0, except for A20 and A02, which we both set equal to the constant c. Now, in addition to the PDE dynamics, we also have, of course, boundary conditions and continuity constraints. The boundary conditions we represent using an operator B in this format. I will get back to that in a minute. And for the continuity constraints, we will assume the PDE state to be second order differentiable in both spatial variables. Now, this is not strictly necessary. We make this assumption only for clarity of this presentation, but in general we can also include constraints requiring this state to be, for example, first order differentiable in each spatial variable. Returning then to our boundary conditions, we note that for our 2D heat equation we have 4 boundary conditions, and yet we represent them using a state of 8 boundary values. So where does that come from? Well, we want to be able to represent a very general class of boundary conditions, and to do so we use this full boundary state lambda BFU. So this full boundary state really collects all allowed derivatives of the PDE state at any point along the boundary of the domain. As such, it will be quite complicated, and we would like to simplify it to an extent that we can. Now, to this end, we will represent the boundary conditions in a minimal manner. So what does that mean? Well, for example, if we want to enforce Dirichlet conditions on the left edge, so if we want to set the PDE state equal to 0 along the left edge of the domain, then we note that we can express the PDE state on this edge into 3 terms, namely the value of the PDE state on the lower left corner, the derivative of the state on the lower left corner, and then the second order derivative of the state along the left edge. Now, since our PDE state is only second order differentiable in both spatial variables, we cannot decompose the state any further, and therefore representing the boundary conditions using these 2 corner values and the second order derivative would be a minimal representation of the boundary conditions. Now, of course, we can also do something very similar for, say, Neumann conditions, also decomposing the spatial derivative of the PDE state in these 3 terms. And doing this for every boundary and for every allowed derivative of the PDE state at every point along the boundary, we can collect all the values into a single vector lambda BFU. So note, for example, that we do not include the full PDE state on the left edge in this full boundary vector, but we do include the second order derivative of the state along this edge, as this is sufficient for us to represent the desired boundary conditions. Now, using this full boundary state, we can then represent the boundary conditions in this format, where we will allow B here to be a partial integral operator. However, in many cases, like for these Dirichlet or Neumann conditions, we can choose B here to be just a matrix. Now, similarly to how we decompose the PDE state along the boundary of the domain, we can also decompose the PDE state on the interior of the domain using Cauchy's rule for repeated integration in 2D. And doing this, we arrive at this beautiful expression here, where you note that all the first terms are expressed in terms of boundary values of the PDE state. And only this last term here varies on the interior of the domain. Now, since our PDE state is only second-order differentiable in both spatial variables, we cannot decompose the state any further than this, and we refer to this second-order derivative of the PDE state as the fundamental state. Now, a crucial property of this fundamental state then is that it's completely free of the boundary and continuity constraints imposed upon the PDE state. So where the PDE solution, and so the PDE state, has to satisfy certain boundary and continuity constraints, the fundamental state does not. Then we have a direct map from the PDE state to the fundamental state using these differential operators. And we have a map from the fundamental state to the PDE state, which includes these boundary values. What we want to do then is impose our boundary conditions in order to get rid of these boundary values, and thus retrieve a direct map from the fundamental state back to the PDE state. To this end, we note that each term in this expression can be represented using a partial integral operator. Therefore, including all these boundary values into a single vector of core boundary vectors lambda BCU, we can express the PDE state in terms of this core boundary vector and the fundamental state u hat using pi operators k1 and k2, yielding this expression over here. Now, since we can do this at any point x, y within the domain, we can also do this on the boundary of the domain. And it follows that we can express the full boundary state in terms of the core boundary state and the fundamental state using pi operators h1 and h2. Then we can impose our boundary conditions, which are expressed in terms of this full boundary state, and then through some simple algebra, we can derive an expression for the core boundary state in terms of the fundamental state, and therefore an expression for the PDE state in terms of the fundamental state as well, using a pi operator t. So this here is really the crucial result at the basis of this entire methodology, namely that given a set of well-posed boundary conditions, so given an operator b such that bh1 here is invertible, we can express the PDE state directly in terms of the fundamental state using a pi operator t. That is, we have a map mapping a state u hat, which is completely free of boundary conditions and continuity constraints, to a state u which satisfies the desired boundary conditions and continuity constraints. Now, using this relation between the PDE state and the fundamental state, we can derive an equivalent representation of our standardized PDE as a partial integral equation, or pi. Now note here that the composition of this differential operator A, defined by our matrices A00 and A22, and our partial integral operator T, can be proven to be a pi operator. Therefore, both T and A here are pi operators, and so our partial integral equation representation is completely parameterized by pi operators as desired. In addition, the fundamental state in the pi representation is free of the boundary conditions and continuity constraints imposed upon the PDE state in the PDE representation, and therefore we can test stability of a partial integral equation without having to explicitly account for these additional constraints. In particular, for a given partial integral equation, we can parameterize a Lyapunov function by a pi operator p, and then the derivative of this Lyapunov function along solutions to the system is parameterized by yet another pi operator q. Now we note here that negativity of this derivative is equivalent to negativity of this operator q here, and therefore we can verify stability of the system by verifying feasibility of this linear pi inequality, which is thus inequality constraints on the pi operators p and q. Now to enforce these inequality constraints, we will parameterize our pi operators by matrices. That is, for a given pi operator z and a matrix P, we define the associated pi operator P in this manner. Then, if this matrix P is positive definite, then so too is the associated operator P. And thus, if we can find a positive definite matrix P and a negative semi-definite matrix Q, such that we can decompose our pi operators P and Q using these matrices P and Q, then that proves stability of our partial integral equation and therefore stability of the associated PDE. So with that, we can actually test stability of linear 2D PDEs, combining all of these steps. Now we've actually implemented this methodology in the MATLAB toolbox PIETOOLS, allowing this to be tested more easily. In particular, to test stability of a 2D PDE, we first have to represent the system in the standardized format by the matrices A, I, J, and the operator B. Then we have to convert the PDE to an equivalent partial integral equation defined by pi operators T and A. And then we can test stability of this partial integral equation by verifying feasibility of this linear pi inequality, where we parameterize these pi operators by matrices. Now, using PIETOOLS then, we can derive an equivalent partial integral equation representation of our 2D heat equation. So note here that where we have second order spatial derivatives in our PDE representation, in the pi representation we only have first order integrals along each spatial variables, which is really one of the strengths of the pi representation. Now to test stability then, we can add an advection term to the equation, parameterized by a value lambda. Then using PIETOOLS, we can verify stability of the system for a value of lambda very close to the analytic stability bound of 2 pi squared. Final example, for a wave equation where we have a second order temporal derivative, we can decompose the state into two components, resulting in a system with only first order temporal derivatives. Then in this format, we can convert the system to a partial integral equation, which looks like this. And then we can also verify stability of this system using PIETOOLS. And with that, I would like to conclude the presentation with this final note that using this method, we can test stability of linear 2D PDEs as an LMI. And we are working hard to extend this method also to other problems such as H-infinity optimal control and estimation. In addition, we are working on a new release of PIETOOLS that includes an easier user interface as well as a user manual for the 2D PDE implementation. With that, I would like to thank you all very much for your attention.